Fine. Let's start. Number 10. Sirius B. Look up on a clear winter night and find the brightest star in the sky. That's Sirius. It's been the brightest thing out there for as long as humans have had eyes to notice, worshipped by the Egyptians, used to mark the seasons, tangled up in 1,000 years of mythology. But here's what almost nobody tells you. Sirius isn't one star. It's two. And the second one is a monster hiding in plain sight. Its name is Sirius B, and it's the closest example we have of one of the strangest objects in the universe, a white dwarf. To understand why it's strange, you have to understand what it actually is. Sirius B contains about the same amount of material as our entire sun, roughly 1 solar mass, but it's been crushed down into a ball only about 12,000 kilometers across. That's smaller than the Earth. You could, in principle, roll this thing across the face of our own planet, and it would fit. Now sit with that for a second, because it's easy to say and hard to feel. A whole sun, squeezed smaller than Earth. The density is almost obscene. If you could scoop up a single teaspoon of Sirius B and set it on your kitchen table, that teaspoon would weigh several tons. It would punch straight through the table, through the floor, through the foundation, and keep going. This is not exotic matter from science fiction. This is a real star, 8.5 light years away, and it is the nearest thing of its kind. And here's the part that should genuinely stop you. What holds it up? A normal star, like our sun, holds itself up with heat. Fusion in the core pushes outward, gravity pulls inward, and the two fight to a standstill. But Sirius B is dead. There's no fusion anymore. The fire went out. By every rule of ordinary physics, gravity should have kept crushing it down to nothing. It didn't. Because at that density, a quantum rule takes over, something called electron degeneracy pressure. In plain terms, the electrons inside the star physically refuse to be packed any tighter. It's not heat holding the star up. It's a law of quantum mechanics. A rule about how much you can crowd particles together before reality itself says no. And it gets better, because Sirius B did something no star had any business doing. It proved Einstein right. General relativity predicts that light climbing out of a strong gravitational field gets stretched. Its color shifted toward the red. On a normal star, the effect is tiny, almost impossible to measure. But Sirius B's gravity is so intense that its own light comes out visibly stretched. Back in 1925, an astronomer named Walter Adams measured exactly that, and it was hailed as one of the first confirmations of Einstein's theory. Almost a century later, in 2018, the Hubble Space Telescope measured it again with brutal precision, a redshift of 80.65 kilometers per second, matching the prediction almost perfectly. Think about what that means. A dead star, the burnt-out corpse of something that used to shine, is so dense that you can watch it bend the rules of space and time just by looking at the color of its light. And this is the friendly one. This is the example we point to when we want something recognizable. It only gets weirder from here. A single teaspoon that could crush a house, held together by a quantum technicality, quietly bending starlight for 100 years while everyone stared at its brighter sibling and never noticed it was there. Number 9. Lucy, the diamond star. 48 light years from here, in the southern constellation of Centaurus, there is a diamond the size of a planet. I want to be clear that I am not being poetic. I mean an actual crystal, made of carbon, roughly the size of the Earth. Astronomers found it, studied it, and nicknamed it Lucy, after the Beatles' song, Lucy in the Sky with Diamonds. Its boring catalog name is BPM 37093. But nobody remembers that, because the diamond star is a much better name for the largest jewel in this corner of the galaxy. Here's how you make one. White dwarfs like this are the leftover cores of stars that ran out of fuel. Inside, they're mostly carbon and oxygen, the ash of billions of years of fusion. When they first form, they're blisteringly hot, tens of thousands of degrees. But a dead star has no way to make new heat. So, very slowly, over billions of years, it cools. And when carbon under that kind of unimaginable pressure gets cold enough, it does something familiar. It crystallizes. It locks into a rigid, ordered lattice. The same basic process that turns carbon into diamond deep inside the Earth, happening across an entire stellar core. In 2004, a team using the Whole Earth Telescope, led by an astronomer named Antonio Canian, worked out that a huge fraction of Lucy had already crystallized. Some estimates put it as high as 90%. And when you run the numbers on how much carbon we're talking about, the figure gets ridiculous. The crystalline mass comes out to something like 10 billion trillion carats. There is no jeweler on Earth who could weigh that. There isn't a scale in the universe you could put it on. It's a diamond you measure in units of planet. But here's the thing that turns this from a fun fact into something that sits with you. Our sun is going to do this too. Billions of years from now, after it swells into a red giant and sheds its outer layers, what's left of our star will be a white dwarf, a carbon core, slowly cooling. And given enough time, it will crystallize, just like Lucy. The sun that gave us every sunrise, every harvest, every warm afternoon, will end its existence as a colossal, cosmic diamond drifting in the dark. So when someone tells you diamonds are forever, they're underselling it. Some of them are the tombstones of stars. Number 8. AR Scorpii. About 380 light-years away, there is a dead star that behaves like a weapon. For decades, astronomers had a rule about a certain kind of cosmic lighthouse. Pulsars, those rapidly spinning stars that sweep beams of radiation across the sky like a cosmic lighthouse, were supposed to be neutron stars, the even denser cousins of white dwarfs. That was the deal. If you saw that machine gun pulse of energy, you were looking at a neutron star. Full stop. Then, in 2016, a team led by an astronomer named Tom Marsh looked at a system called AR Scorpii and found something that broke the rule. At the heart of AR Scorpii is a white dwarf, an Earth-sized dead star, and it is spinning. Fast. It completes a full rotation once every 117 seconds. Just under 2 minutes. Now picture a body the size of a planet containing the mass of a star, whipping around on its axis in less time than it takes you to make a cup of coffee. And it's not alone. It has a companion, a small red dwarf star, orbiting close by. And here's where it stops being astronomy and starts being violence. That spinning white dwarf has a ferocious magnetic field. As it rotates, it drags that field around with it, and it lashes its companion, a red dwarf star, with beams of radiation and high-energy charged particles, over and over, once every rotation. The companion star gets whipped on a schedule by its dead neighbor, and the whole system lights up in response, pulsing in a rhythm you can track from radio waves all the way up to ultraviolet. It's the first white dwarf pulsar ever found, a brand new class of object. What makes it defy the textbook is where the energy comes from. Neutron star pulsars are powered by their own insane density. AR Scorpii isn't dense enough for that trick. Instead, it's powered by its own spin. It's slowly, measurably slowing down, bleeding its rotational energy out into those beams. It is a flywheel the size of a planet, winding down over centuries. And every turn of that flywheel, it reaches out and strikes the star next to it. Astronomers had said this shouldn't happen, that a white dwarf couldn't run this particular machine. AR Scorpii didn't get the message. Somewhere out in Scorpius, A dead star is beating its living neighbor with invisible light, and it has been doing it, faithfully, every 2 minutes, for longer than humans have existed. Number 7. The planet that outlived its star. Here's a question you'd think has an obvious answer. When a star dies, what happens to its planets? For a long time, the assumption was simple. They die too. When a star like our sun runs low on fuel, it doesn't go quietly. It swells. It becomes a red giant, ballooning outward until it swallows its closest planets whole. Mercury, Venus, probably Earth, all of them consumed in fire. Anything that close gets vaporized. That's just how it goes. And then, about 80 light years away, we found WD 1856b, and it made a mockery of the whole idea. WD 1856 is a white dwarf, a dead star. And orbiting it, astronomers found a planet, a gas giant about the size of Jupiter. Discovered in 2020 using NASA's TESS telescope and Spitzer, this planet circles its dead star once every 34 hours. 34 hours. Our Earth takes a year. This thing does a full lap in less than a day and a half, whipping around so close that it sits right inside the zone where the star, back when it was a swollen red giant, should have destroyed it utterly. And that's the impossible part. At that distance, during the red giant phase, this planet should have been inside the star. It should be gone. Ash. Instead, it's still there. Intact. 7 times larger than the tiny Earth-sized corpse it orbits. Let that image land. A planet. 7 times bigger than its own star, circling a dead ember in the dark. So how did it survive? The best answer is that it didn't survive there. It survived somewhere else. Astronomers think the planet originally orbited much farther out, safely beyond the red giant's reach, and then, after the star died and shrank into a white dwarf, something flung the planet inward. A gravitational nudge, maybe from another unseen object, that dropped it into this tight, impossible orbit. It's a refugee. It watched its star die from a safe distance, and only afterward moved into the ruins. There's something almost haunting about it. A world drifting through the aftermath of a catastrophe, settling into the quiet, cooling glow of the thing that used to be its sun. Not destroyed, just orphaned, and strangely stubbornly still here. Number 6. The star caught in the act. We just talked about a planet that survived its star's death. Now, let's talk about one that didn't, and about the fact that we are watching it happen right now, in real time. In 2015, an astronomer named Andrew Vanderberg was looking at data from the Kepler Space Telescope, studying a white dwarf called WD 1145 plus 017, and he noticed the star was flickering, dimming, in a strange, irregular repeating pattern. When something passes in front of a star and blocks its light, we call that a transit, and it's how we find most planets. But this wasn't a planet. Planets make clean, smooth, predictable dips. This was messy, ragged, wrong. What he'd found was a graveyard in progress. Orbiting that white dwarf, incredibly close, were the shredded remains of what used to be a small planet or an asteroid. Multiple chunks, maybe 6 or more, each on its own tight orbit, circling the star every 4.5 hours or so. And these chunks are not stable. They're so close to the dead star that its gravity is physically tearing them apart, boiling them away, wrapping each fragment in a long comet-like tail of dust and vaporized rock. That dust is what makes the star flicker. As each debris cloud sweeps in front of the white dwarf, it blocks a chunk of the light, sometimes as much as 60% of it, in dips that are deep and long and irregular. And because the debris is actively evolving, the pattern changes from month to month. Astronomers can watch, night after night, as a planetesimal is ground into powder and rained down onto the surface of a star. Think about that. Somewhere out there, A solar system is being cremated, and we have a front row seat. This is what a lot of white dwarfs are quietly doing. They're not just dead, they're cannibals, dragging in the leftover worlds of their own planetary systems and consuming them one by one. WD 1145 is simply the one we caught mid-meal, the first time we ever saw the destruction as it was actually happening. And here's the quiet, uncomfortable thought underneath it. When our own sun dies, when it becomes a white dwarf, it may do exactly this. It may reach back into the wreckage of the solar system and pull in whatever pieces of the Earth are left. The universe doesn't just kill worlds. Sometimes it eats them afterward. Number 5. The star on the knife's edge. There is a white dwarf out there that is living on borrowed time, balanced on the exact edge between two impossible states, and it might not survive being looked at for too much longer. In 2021, a team at Caltech, led by an astrophysicist named Ilaria Caiazzo, announced the discovery of the smallest and most massive white dwarf ever found. Its name is ZTFJ 1901 plus 1458, and everything about it is extreme. Start with the mass. It contains about 1.35 times the mass of our Sun. That's more than any white dwarf we've ever measured, and it's dangerously close to a number that acts like a hard ceiling for these stars. Now, here's the strange, counterintuitive thing about white dwarfs. The heavier they are, the smaller they get. More mass means more gravity, which means more crushing, which means a tinier star. So this, the most massive white dwarf we know of, is also the smallest. Its radius is only about 2,140 kilometers. That's roughly the size of our moon. A star heavier than the sun, packed into a ball the size of the moon. And it's not just sitting there, quietly. It's spinning once every 7 minutes, and it's wrapped in a magnetic field about 1 billion times stronger than the sun's. This is a small, dense, furious object, spinning and blazing with magnetism, and it's sitting right at the limit of what a white dwarf is even allowed to be. Because here's the knife's edge. There's a maximum mass a white dwarf can have, and this star is nearly at it. If it were just a little heavier, electron degeneracy pressure, that quantum rule holding it up, would lose the fight. Gravity would win, and the star would face a choice. It could collapse into a neutron star, crushing even further into something the size of a city. Or it could detonate entirely, blowing itself apart in a supernova. This white dwarf is poised at that exact tipping point, the last stable moment before one of those two fates. Astronomers think it got so massive because it's actually two white dwarfs that merged into one, and now the combined star is teetering on the brink. We may be catching it in the final chapter before it stops being a white dwarf at all, a star holding its breath, and one day it's going to exhale. Number 4. The star wearing its own guts. Everything you see when you look at a star is the surface, the atmosphere. For our sun, that's hydrogen and helium, the light elements, floating on top and hiding everything underneath. You never see a star's interior. Its core is buried under thousands of kilometers of gas, locked away where no telescope can reach. Except once we found a star that was inside out. A white dwarf whose surface is made of the stuff that's supposed to be deep in the core. Its name is SDSSJ 1240 plus 6710, and looking at it is like looking at a body with its skin removed. Instead of hydrogen and helium, its atmosphere is dominated by oxygen, along with neon, magnesium, and silicon. These are heavy elements, the products of advanced nuclear burning, the kind of material that belongs at the heart of a star, not on its face. So the obvious question is, what stripped this star down to its guts? And in 2020, an astronomer named Boris Ganzika and his colleagues found a chilling answer buried in the chemistry. They studied the star's light in detail, and they found carbon, sodium, and aluminium, but they did not find iron. And that absence is the whole story. When a white dwarf explodes as a supernova, the runaway nuclear burning cooks its way up the periodic table, and it ends by producing iron group elements. Iron is the signature of a completed explosion. This star has the ash of nuclear burning all over it, but no iron, which means the explosion started and then stopped. The fuse was lit. The burning tore through part of the star, transmuting its insides, oxygen, sodium, the works. And then, for reasons we still don't fully understand, it fizzled out before it could finish the job. This is a failed supernova. A star that began to detonate and somehow survived the attempt, left half transformed, its buried interior blasted up to the surface for us to read, like a coroner's report. And it's not sitting still either. The event that nearly destroyed it also kicked it, and now it's tearing through the galaxy at something like 900,000 kilometers per hour. A scarred, half-burnt survivor, running from the explosion that almost was, wearing the evidence of its own near death on the outside. We didn't just find a dead star. We found the crime scene, and the body was still warm. Number 3. The zombie star. If a failed supernova unsettles you, this one should genuinely get under your skin. Because there's a star out there that didn't just start to explode and stop. This one exploded, all the way, a real thermonuclear supernova, and then walked away from it. Its name is LP40-365, and astronomers call this kind of object a zombie star because the description writes itself. It died, and it kept going. Here's the setup. Some supernovae, a rare, peculiar type, don't fully destroy the star that explodes. Most Type 1a supernovae obliterate their white dwarf completely, leaving nothing behind but an expanding cloud. But there's a weaker variety, where the nuclear detonation only partly disrupts the star. The blast goes off, tears through it, flings most of it into space, and yet somehow a battered, partly burnt remnant survives the explosion. LP40-365 is one of those survivors. In 2018, using data from the Gaia Space Telescope, a team led by an astronomer named Roberto Ratti pieced together its story. And what a story it is. First, the composition. This star isn't made of normal star stuff anymore. Its surface is a strange brew of oxygen, sodium, and magnesium. Nuclear ash, the leftover soot of a thermonuclear blast. It's not a star wearing an atmosphere. It's a cinder wearing the residue of its own detonation. Second, the speed. The explosion didn't just fail to kill it. It kicked it hard. LP40-365 is now screaming through the galaxy at around 850 kilometers per second, so fast that it's no longer bound to the Milky Way at all. It's on a one-way trip out, destined to leave the galaxy entirely and drift into intergalactic space forever. And the blast that did this, it went off somewhere between 5 and 50 million years ago. So this thing has been running for a very long time. A burnt-out fragment of a star that experienced its own death and refused to finish dying. Picture it. The detonation lights up. The star is torn nearly to pieces, and out of the fireball, a chunk survives, flung outward like shrapnel, glowing dull and strange with the chemistry of its own destruction, and it just keeps going, out past the edge of everything it ever knew, alone, forever. A star that was killed and didn't stay dead. The universe apparently has zombies, and they run fast. Number 2, the star that broke the one rule. Everything we've talked about tonight sits on top of a single number, one of the most trusted numbers in all of physics. It's called the Chandrasekhar limit, and it is the reason white dwarfs are so orderly, so predictable, so useful to astronomers. Let me explain why it matters, and then let me tell you about the star that seems to have broken it. Back in the 1930s, a young physicist named Subramanian Chandrasekhar worked out the math for how much mass a white dwarf could hold before its own gravity overwhelmed that quantum rule holding it up. The answer he got was about 1.4 times the mass of the Sun. Below that, you get a stable white dwarf. Push it above that, add too much mass, and the star can't support itself. It collapses, or it explodes. 1.4 solar masses. That's the ceiling. And it's such a reliable ceiling that when white dwarfs do explode as supernovae, they tend to do it at almost exactly the same mass, releasing almost exactly the same amount of energy. That consistency is a gift. It means these explosions all shine with nearly the same brightness, which lets astronomers use them as measuring sticks to gauge distances across the entire universe. The Chandrasekhar limit is one of the load-bearing walls of modern cosmology. And then, in 2003, a supernova went off that shouldn't have. It was discovered from the telescopes on Mauna Kea in Hawaii, and researchers at the University of Toronto studied it. It was a Type 1a, the white dwarf kind. But when they measured how bright it was, and how much material it must have contained, the number came back wrong. This white dwarf appeared to have been carrying around 2 solar masses when it detonated. 2, not 1.4. A third heavier than the limit that is supposed to be unbreakable. They nicknamed it the Champagne supernova, and it sent a quiet shockwave through the field. Because if the Chandrasekhar limit can be broken, some of those measuring sticks aren't quite as reliable as we thought. So how did it happen? There are a couple of leading ideas. Maybe the white dwarf was spinning so incredibly fast that the extra centrifugal force helped hold it together past the normal limit, letting it pile on more mass before going off. Or maybe it wasn't one star at all, but 2 white dwarfs that spiraled together and merged, briefly forming a single overmassive object that immediately exploded. We still don't know for certain. What we do know is that the one hard rule, the number we built, part of our understanding of the cosmos on top of, has at least one glaring exception out there. A star that looked at the ceiling everyone said was unbreakable and went straight through it. Number 1, the bomb in our backyard. We've saved the most unsettling one for last. Not because it's the most violent, because it's the closest. For all of human history, supernovae have been things that happen to other stars. Far away, long ago, safely abstract. We see them as points of light, flaring up in distant galaxies, or as ancient expanding clouds, the leftovers of blasts that went off before we existed. We have never been able to point at a specific pair of stars and say, that one right there is going to explode, and here's where it's going to happen. Until now. In April of 2025, astronomers announced a discovery published in the journal Nature Astronomy. They'd found a system called WDJ 181058. It's a pair of white dwarfs, 2 dead stars, locked in a tight orbit around each other. And this pair is different from every other supernova candidate we've ever found, for one simple reason. It's guaranteed. The 2 stars together weigh about 1.56 solar masses, comfortably above the Chandrasekhar limit. They are spiraling toward each other, and one day they will merge. Or more precisely, they will detonate in a double explosion just before they merge, and become a Type 1a supernova. This isn't a maybe. It's a matter of physics and time. And here's the number that matters. This system is only about 150 light-years away. In galactic terms, that's next door. That's our neighborhood. The 2 white dwarfs are so close together that they complete a full orbit around each other in just 14 hours, circling at a distance of about 1/60th of the gap between the Earth and the Sun. 2 burnt-out stars, waltzing that fast, that close, with more than enough combined mass to blow themselves apart. The first confirmed future Type 1a supernova, and it's practically on our doorstep. Now, before you look up nervously, here's the reassurance. This isn't happening soon, and it isn't going to hurt us. The merger is something like 23 billion years away. That's longer than the current age of the universe. And even when it goes off, at 150 light years, it would be a spectacular light in the sky, not a threat to life on Earth. So you can breathe. But I want you to sit with what this actually means, because it's bigger than the safety math. For the first time, we have proof, concrete, confirmed, in our own backyard proof, that the recipe for one of the universe's most powerful explosions is sitting quietly nearby, already assembled, just waiting for time to run its course. These dead stars, these white dwarfs, are the most reliable bombs in the cosmos, and they are everywhere. They are the future of most stars in the sky, including eventually our own. Our sun will die and shrink and become a white dwarf and cool and crystallize into a diamond in the dark. It won't explode. It's alone. There's no partner to push it over the edge, but it will become one of these quiet, dense, patient corpses, scattered across a galaxy that is slowly filling up with them. That's the thing about white dwarfs. We started tonight with Sirius B, a curiosity, a teaspoon that could crush a house. And we've ended here, with the realization that these objects aren't exotic exceptions at all. They're the end point, the place where stars go when the fire finally runs out. Most of the lights you see when you look up are, in the deep future, destined to become exactly this. Tiny, dense, silent, bending light, growing diamonds, occasionally waking up to whip a neighbor, or devour a planet, or detonate without warning. The sky is quietly filling with the dead, and some of them, it turns out, are far closer and far stranger than we ever imagined. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.